All right, welcome back to your first class in November. We didn't have a class on Thursday. You guys had a long weekend, which I hope you enjoyed. And today we're going to finish chapter or unit 3. I'm going to leave a little bit of unit 3 at the end to do at the end of the month, but we're going to finish this section. I think it's 3.6, and then move into chapter 4. Now, before I get started, you guys have a lab this week, but your lab is online, and your lab is basically the first 2 sections of chapter 4. So between today and tomorrow's class, we will get through those first 2 sections in chapter 4. So after tomorrow, tomorrow is Tuesday, you guys will have all of the information you need to do your lab this week. Now remember, your lab is online, and we're giving you the entire week to do that lab. So I had 1 student out of 60 do the lab yesterday. Most of you haven't done it. Well, I haven't checked actually this morning, but if you haven't done the lab, or if you've looked at the lab and you don't know what to do, today and tomorrow, we are going to cover everything you need to know for that lab. So after tomorrow, Tuesday, you will be ready to complete lab number 7. All right, so I just want to take a couple of minutes to finish off section 3.6, and then we'll get into chapter 4. I just today uploaded the notes to chapter 4. If you don't have them printed, that makes sense because I only put them up a little while ago. But you can, if you have a printer or access to a printer, they are there for you to print today, tomorrow, whenever you want. You won't need to have them printed today. I have the answers pretty much calculated for you. Oh, except one example. I'm going to give you a practice problem before we finish. So let's get started. Last week on Wednesday, we talked about intermolecular forces. We looked at hydrogen bonding, dipole-dipole, and London dispersion, and even ionic bonding, and we did this example, this one here. So today, I'm just going to finish off this section talking about water. Now, this section is useful, or it's, I guess, more so an introduction for anybody going to eventually take 2770. This is a chemistry course that any of you in environmental health and safety, you will do this course. For my engineering students or medical science that are not in environmental health and safety, you will not have to do this course. Chemistry 2770 is an environmental chemistry course with a focus on water quality. Okay, oops, I got a phone call. I'm not going to take it though. I'll mute my phone. Okay, so water. This, again, in Chemistry 2770, most of that course is based on water quality. And water is such a cool chemical. Even though water is the most common chemical in our lives, from a chemistry point of view, like a physical property point of view, it is such an interesting chemical. It's really amazing. And most of the amazing features or properties of water are due to the hydrogen bonding. So let's look at 3 chemicals. We'll look at HF, hydrogen fluoride. We'll look at NH3, ammonia, and then we'll look at water. HF, when you have a sample of hydrogen fluoride or HF, it basically only forms 1 hydrogen bond between each of the molecules, and it has a boiling point of 19.5, pretty high. Most small covalent compounds have low boiling or melting points. NH3, the boiling point of NH3 is again very low. Just let me check something actually. Ammonia boiling point. Yeah, so the boiling point of ammonia is negative 33. You don't have to memorize these numbers, don't worry. Again, very low. And ammonia can form one hydrogen bond. You don't need to know these diagrams, don't worry. All you need to know is that water, of all the simple covalent compounds, water can form the most hydrogen bonds. So you can see circled in red, all of those hydrogen bonds around the water molecule. Because water can form so many hydrogen bonds, it has a very high boiling point. Compared to simple molecules, the boiling point of this is very, very high. Okay, so why is that? Well, the answer is there are more hydrogen bonds in water than most other chemicals. What this means is the boiling point is much higher. Remember what heating and boiling are. We did this, I think, in lab maybe 3 or 4, maybe 5, I can't remember now, but we talked about heating and cooling of elements or compounds, sorry. When you heat up a chemical compound, you're adding energy, and the energy is converted into kinetic energy. And then again, this is all from your lab before, I think it was lab 4 or 5. The kinetic energy increases as you heat something up, and then to change its phase, meaning to boil or to melt something, you need extra energy to change that phase. Because water is so strongly, or has such strong intermolecular forces, the energy it takes to break those hydrogen bonds to change the phase of the chemical is very high. So a lot of energy is needed to break the hydrogen bonding in water. And because you need a lot of energy, water has a very high boiling point. So what does this mean? Well, in water, water is such a useful chemical in industry, the medical industry, I'm sure, but mostly in like the engineering type of industries. Water is typically used as a coolant. It's a chemical, or well, it's a solution, not a solution. It's, I guess, yeah, I guess like you say a chemical that industries use to absorb heat from high energy processes. It's a coolant. This is something in environmental chemistry we'll talk about again, because this is a form of pollution. Heat pollution is caused when you are dumping hot water into something like an ocean or river or lake or stream. But that's for another course. But yeah, water, because it can absorb so much energy, it's used typically as a coolant in many industries. Basically, it absorbs extra heat from reactions. You don't need to know that, of course, but just an interesting fact. The last fact I'll mention for water, and then that's it, is water is also unique. And again, this is definitely something we'll talk about in 2770. Water is also unique because it's the only chemical where the solid form floats in the liquid form. Now, just kind of think about what I'm saying there. If you had a solid sample of iron and you dropped it in liquefied or molten iron, the solid will sink. And the same is for every chemical. The solid form is typically more dense than the liquid form. But why does water float? Well, why does solid water or ice float? Well, ice has a smaller density than water. When water freezes and turns into a solid, the volume actually expands. It expands about 9%, which again, you don't need to know, but in chemistry 2770, we would look more into this. But the volume of ice expands. It gets bigger than the liquid water. And this is because it tries to maximize the hydrogen bonding as you freeze it. So they kind of spread apart a little more. They take up more volume, and that means they have a smaller density. That's why ice floats. It's really interesting. So I mean, if you've ever, I mean, I shouldn't say if you've ever, any of you that's been to McDonald's or a movie theater and you got a fountain drink like a Pepsi or 7-Up, and they put ice in it. In theory, that ice should sink to the bottom. But again, water is such a special chemical. The density actually gets larger when it freezes, and that is because it tries to maximize the space or to form more hydrogen bonds. Okay, so that's really it for chapter 3 for now. I say for now. This section, what we're going to do is we're going to look at solutions first. Solutions are in chapter 4. So what I'm going to do is get into chapter 4 today. We'll just do a little, maybe 15 minutes, an introduction. And then after we're done chapter 4, we'll come back to section 3.7 for acids and bases. Acids and bases typically in chemistry 1120 and 1121 are solutions. So I'm going to cover solutions first, and we'll come back to this after. Sorry, I have a really good point in the chat there. Is the student says, but Pepsi is not water. You're correct. It's not exactly water, but Pepsi is definitely like, I don't know, 95% water. And then the rest is sugar and different chemicals to make it, flavor chemicals and sugar. So, why does ice still float on Pepsi? Well, again, Pepsi is 99%, well, maybe not 99, but mostly water. I'm going to just see. I just Googled it. So regular soft drinks are over 90% water. Diet soft drinks, like, Diet Pepsi, Diet Coke, Coke Zero, are more than 99% water. So yeah, ice still floats on Pepsi or 7-Up or Coke because it is mostly water. Good question. So guys, I'm gonna share a new PowerPoint with you. We're gonna do solutions first, and we'll come back to this. So we'll do this after chapter 4. All right, so I'm going to share a new screen with you. I guess I should open up my notes first. And we'll just do a little introduction of chapter 4. There are a few chapters left, and I know it's November 1st, or actually, sorry, November 2nd, but all of the chapters that we have left are significantly shorter than chapter 3. Chapter 3 was about 3 times the size of chapter 4. All right, hold on now. I gotta do something and share my screen. All right, I'm excited. This is maybe one of my favorite chapters, Unit 4, mole calculations. So this is what you'll need for Lab 7. And you'll be ready, like I said, for Lab 7 after tomorrow's class. You will have everything you need to do Lab number 7. Okay, so section 4.1. Avogadro's number. This is a really important section. Basically, I'll do this section in 10 minutes, and then we'll get into 4.2, and that's it. All right, so in this section, we're going to look at atomic mass, Avogadro's constant, and then the most important thing is we're going to look at or define what is a mole. And if you can't remember what that is, I'll explain it in just a short minute. The first things first, what is atomic mass and what does it mean for mole calculations? If you can remember from chapter 1, I'll talk about this on the next slide, but chapter 1, we mentioned that atomic mass is on your periodic table. And in the early days of chemistry, remember what a mass is. A mass is a number relative to another object. So like a kilogram is related to this object. right? All measurements are relative to something else. So when we were coming up with atomic masses, chemists had to decide what element they were going to use as a reference. And they eventually decided on carbon. Now, you don't need to know this, okay? You don't need to memorize this, but the masses, the atomic masses of all the elements are based on 1/12 the mass of carbon 12. And you can see the number on bottom here is our atomic mass. Your periodic table has the atomic masses listed, and on your periodic table, we have actually an extra couple of significant figures there, but we'll talk about that in a few minutes. Okay, so the big thing today, why are you here today? Well, you have a lab this week on mole calculations. What is a mole? Well, in chemistry, a mole, or I shouldn't say in chemistry, I guess I should say in science, a mole is one of the 7 base SI units, the International System of Units. So remember, like for mass, the SI unit is kilogram. The SI unit for length is meter. The SI unit for temperature is actually Kelvin. Well, the SI unit for amount, like counting, is the mole. A mole is amount of substance that contains as many molecules as there are atoms, that sounds complicated, in exactly 12 grams of carbon 12. Now, that's not the definition you really need to know. The definition of a mole that you really need to know is here. The mole, so how much is 1 mole? The mole is 6.022 times 10 to the 23 particles or things. These could be atoms, molecules, ions, formula units. It could be hair on your head or stars in the universe. All right. So this number, like you guys might be thinking, what a weird number, 6.022 times 10 to the 23. Well, this is known as Avogadro's number, and it's equal to the number of atoms in 12 grams of carbon 12. This number is in your data book. You do not have to memorize it. It's a constant. It's like gravity or pi, the speed of light, for example. It's a number that doesn't change. It's a constant. Okay, before I move on to the next slide, I just want to explain something to you, maybe to help you wrap your heads around this. Why use that number? Why use the mole? What's the purpose? So 1 mole is 6.022 times 10 to the 23, so very large number, particles. Oops. Okay, sorry about that. So, let's relate this to something in real day life or everyday life. If you say your mom, dad, your brother, sister, whoever asks you to go to a store, Almira, Carrefour, whatever, and they say, pick me up or buy me 1 dozen eggs. 1 dozen equals 12 things. So in, baking or in cooking, or we use the word dozen to quickly represent 12 things. If I'm making breakfast for a bunch of people, I might need 2 dozen eggs. That would be 24 eggs. Well, in chemistry, we also use something like a dozen, and we call it a mole, M-O-L. That's the unit, M-O-L. Because samples of elements or chemicals have millions, billions, trillions of particles, like a glass of water, if any of you guys are drinking, a tea or a water right now, like almost unimaginable amount of molecules are in that sample, millions, billions, trillions of particles. Because there are so many particles in a sample, a sample of a chemical, we try to make them smaller by using the mole. So in the lab, I might say you have 2 moles of something. It's a lot easier to say 2 or 1 mole than 6.022 times 10 to the 23. Again, the whole idea is we're trying to really lower the numbers that we're using so they're more manageable. So again, in the lab, you would hear things like 0.1 mole or 1.6 moles instead of gigantic numbers. Yeah, I mean, it's almost infinite. Well, no, I shouldn't. My math friends, my other math teachers would be mad if I said it was infinity. But like for the average person, a number like 6.022 times 10 to the 23 is almost unimaginable. Like it's so big. And I wouldn't say it was infinite because my math friends would get mad at me, but it's really, really big. Okay, so again, the whole purpose of the mole is to use more manageable numbers in chemistry. Instead of using something times 10 to the 25 or times 10 to the 22, we use something manageable. And that brings us to our first formula. Our first formula is useful on your lab 7. So you guys could get started on your lab today if you want to. You have unlimited time for the lab, so you can get started today if you want using this formula. The formula for finding the number of particles of a substance is, in the good old chemistry, nice and confusing, capital N equals little n times NA. Now, look at that formula. There's 3 n's in that formula. There's capital uppercase N, lowercase n, and then an uppercase N with a subscript. The good news for you guys is this is in your data booklet. You don't, in this course, have to memorize the formulas or constants for equations. So this is in your data booklet. Yeah, and I mean, there's a good question in the chat. Why not, different formulas? Well, P in chemistry means pressure, M in chemistry means molarity, and A in chemistry typically means amps or amperes. So I think all of the letters, the physics people already used the letters P, M, and A. So in chemistry, we had to use N. Yeah, it is a good question though. Like, why is this formula? Why would we use N to mean moles? And it's because the other letters of the alphabet were used. A small m would be mass, and a large or uppercase M would typically be moles per liter or molarity. We'll get into that a little later. Now, you guys are expected to know how to rearrange your own formulas. I think most of you guys would be in math right now, or maybe some of you have already done math, but you should know how to solve for particles and how to solve for moles. You should know both of those things. Okay, and again, only one of these formulas is in your data booklet. Let's open up your data booklet. Let's have a look at it. I'll show you where it is. Okay, you can see here I was writing about molar mass in the other class. Let me clear that. Oh yeah, let me share my screen. Okay, so where would that formula be in your data booklet? I think it's on page 8. Yep, page 8. In the general section of your data booklet, there's your formula right there. For your lab number 7, you can do that entire lab using these 3 formulas, or I guess it's 2 formulas and a constant. So you need to know, because the data booklet only gives you 1 formula, you need to know how to rearrange that formula to solve for N. Now let me clear that. Oops, sorry. There we go. So you are expected at some point in this course to solve for moles or N, and we're going to look at that today. All right, let's go back to my PowerPoint. I'm not too much longer today, by the way. Let's look at an example of this. This would be an example that's on your lab today, or this week, I should say. How many particles of copper are in 5 moles? Well, when I do questions like this, I tend to approach them like how I would do a physics example. And I don't know if any of you are in physics, it doesn't matter if you're not, but the way that my old physics teachers and professors used to do these problems is they would identify the information that you are given and then identify what the question is looking for. So what I mean is I'm given the number of moles and it's asking for the number of particles. Okay, so let's assign these guys letters. I know particles is capital N, and I know moles is lowercase n. NA, you will always know. I should say, if I'm going to use English correctly, known. You always know NA. NA, Avogadro's number. That kind of makes sense, doesn't it? AN, Avogadro's number. But this is always known. It's a constant like gravity, pi, speed of light. You know, it's something we always know. So this is pretty easy. It's asking for N. So I'm going to go N is equal to moles times Avogadro's number. This formula is again from my data book. Now, I already have this calculated for you guys. So if you print your notes this week, you'll see this. I just plug my numbers into the formula. I would say 5 moles times Avogadro's number. You'll notice if you guys are, have been practicing in physics or math, the moles cancel. Right here I have mole on the top, here I have mole on the bottom. They cancel, and I'm left with my number of particles. This question, guys, you will only see in Chemistry 1120. After Chemistry 1120, we kind of stopped talking about particles because no true kind of science student or chemistry student really talks about particles after first year chemistry. You typically then start to talk about moles. So Shadan mentioned in the chat, it's easy. Yeah, 5 times Na, Avogadro's number. Nice and easy. Okay, so that is an example that will help you in your lab this week. Let's look at a more realistic example. And I say realistic because typically, again, sorry, I have a good question there. I'll come back to that. But typically in chemistry, we're going to be dealing with moles. So this right here. Somebody just asked, what is the unit? The unit here is particles. You could actually call this atoms as well, but we just use particles for this example. Okay, I think that's what you meant by unit. This is unit 4, but the units for this would just be particles. You could also call it atoms if you wanted. All right, let's look at another example. Now, this one, again, like I mentioned, I'll put a little star here. This is more realistic for chemistry or a chemist person. Oops. Let me highlight again. So here, I am given some information. I am given the number of molecules. Now, remember, atoms, particles, molecules, they're all the same thing. They're N, capital N. The question is asking me to calculate how many moles. So again, kind of going back to this, like I would approach a physics problem, I am given capital N this time, and it's asking for moles or lowercase n. Now, this is where we have a problem with my students who can't remember algebra. N is equal to moles times Avogadro's number. I'm trying to solve for N. So N is equal to, when I rearrange this equation, N over NA. You guys are expected to know how to rearrange this equation. Thank you, Shadan. That's exactly correct in the chat. So I'm going to use this formula. And now, I already have it kind of calculated here. I'm not really happy about how this is written. Okay, sorry. Let me do something here. Hold on, I'll be right back. I'm just going to change something here. I meant to change it before I uploaded it, and it kind of slipped my mind. Okay. Sorry, guys. I'll be ready in 1 second. Just kind of rearranging how I write it. You'll see what I mean in literally 10 seconds. There we go. Okay, sorry, let me share my screen again. You'll see what I mean. There we go. Okay, so sorry. I just put the ends on the left. All right, so guys, this kind of approaches the way of solving this formula by putting the numbers in first and then rearranging it. I'm more of a fan of rearranging it first and then putting my numbers in. So all I'm doing for this question to find moles is I'm taking my number of particles. Let me pick a different color. Bit of a red overload, isn't it? So I'm taking my number of particles and I'm dividing it by Avogadro's number. So 9.12 times 10 to the 24 divided by Avogadro's number would give us 15 moles, or 15.1 moles. Remember your significant figures. All right, so this type of question you would also see in your lab this week. Now, I don't really have many practice problems on this because it is pretty straightforward, but we will be doing practice problems in the next sections. So you'll get a lot more practice with this in the next section, section 4.2. Okay, I'm pretty much done for today. I got a little further with my other class, but that's okay. I just want to introduce this section and maybe leave you with something to consider. So just give me 5 minutes and you guys are free to go. Okay, I'll just kind of introduce this and then we'll finish this section tomorrow. Section 4.2, molecular, formula mass, and molar mass. Okay, so we're looking at molecular mass, formula mass, molar mass. In this section, we're going to calculate the masses of elements and compounds, the masses of moles. We're going to calculate the number of moles and then calculate the number of particles. All of this you will need for lab 7. So after tomorrow, like I mentioned, you'll be ready to do that experiment. Well, it's not an experiment. It's honestly more like an assignment. It's there's no videos to watch or molecules to make like you did in lab 6. You just it's basically an assignment. So remember from unit 1 that the atomic masses on the periodic table, just give me 4 minutes. If you remember back from unit 1, the atomic masses are listed on the periodic table, not the mass number, okay? The atomic masses are listed on the periodic table. So for example, carbon, which I have listed below there, it would look on your periodic table like this. All right, this is called the atomic mass. It's the average of the isotopes of that atom. This number on the bottom, however, is very useful to us, and we're going to need it for tomorrow's class. This number is also equal to molar mass. So those numbers on the periodic table also represent something called the molar mass. The molar mass is the mass in grams of 1 mole of any substance. Molar mass, it's grams per mole. The mass in grams of 1 mole. You can calculate the molar mass for elements, compounds, or ions. You can basically calculate it for anything. All right, I'm almost done. I'm just going to basically show you this example, 2 slides more, and we're finished. So when we write molar mass, and I will explain what this is before we go, we typically use MM to stand for molar mass. So Iman in the chat there, you'll probably like this. Unlike mole, which is N, or particles, which is also capital, well, it's also N, MM means molar mass. So that's really easy to write, MM, molar mass. You don't have to do this, but typically we would put the molar mass of the chemical we're calculating in next to MM in lowercase. So for example, if I wanted to write the molar mass of water, it's 18 point something, something, something. I would say MM and then write H2O next to it. All right, 2 quick slides and we're done for today. So easiest example of life. What if I had to, I asked you, what is the molar mass of, magnesium, Mg? What is the molar mass of magnesium? Well, the molar mass for each element is straight from your periodic table. It's also the same as atomic mass. All right, so how do I find it? Just imagine I asked you to calculate the molar mass of Mg. Well, go to your good friend, the periodic table. Okay, find Mg. And there we go. There's my molar mass. Well, sorry, maybe I circled that too big. Let me zoom in here. There we go. There's our molar mass. It's the same as atomic mass. If I asked you for the molar mass of lithium, 6.941. Hydrogen, 1.00749. Now, this is the finale of today, guys. I'm done after this. What about if it's not an element? What about you need to find the molar mass of a compound? So something like MgCl2. What would you do for this? Or MgNO3. How would you find the molar mass for this? Well, all you need to do, and we're going to practice this tomorrow because I'm out of time, but all you need to do to find the molar mass for a compound is add up the entire masses of each element. This example, and this is my last thing I'll say today, this is a hard example. This is purposefully made to be quite difficult. I have the compound calcium nitrate. If you can remember from chapter 3, naming. How would I find the molar mass of this compound? Well, this compound has 1 calcium. It has, now you got to be careful here, it has 2 nitrogens. Sorry about my dog there. And it has 6 oxygens. Remember, I have this 2 means I have 2 of these. So in total, I would have 1 calcium, 2 nitrogens, and 6 oxygens. Again, if you can't remember where the 6 comes from, it's the 2 times the 3, because I have 2 nitrates, which means if you counted the total, I would have, well, 2 nitrates is 2 nitrogens and 3 oxygens. Once you've calculated the total of each element, you just add them up. It seems a lot harder, or sorry, it might look a lot harder than it is, but it's actually quite easy. Now, guys, I'm out of time today. I don't know why I went long with you guys. I did the same thing with the other class, and we were done like 10 minutes earlier. I guess I think I explained it a little better to you guys, or I hope I did. Why don't, not now, because I have another class and it's 3:17, but if you're not ready to do your lab, you could try these and we'll look at the answers tomorrow. Okay. Another challenge you could give yourself if you wanted to practice this before tomorrow's class is you could also try to name these compounds. Don't forget, chapter 3, you're going to need to know how to name things. So we will do this tomorrow. We will finish section 4.2 tomorrow, and that will mean that you're completely ready to do your lab number 7. Okay, guys, that's it for me. If you have any questions, let me know. I will be uploading this class for sure. So if you've missed, and I haven't uploaded last week as well, but I'll get them up as soon as I can so you guys can look at this. But yeah, I'm done. So thanks, everybody. If you have any questions, let me know. But other than that, that's it for today. Sorry for the long class.